Course, and today we have come to lecture number 10. Then this lecture will be about bus admittance matrix. So in fact we have spent quite a good number of lectures covering the fundamentals, and bus admittance matrix is slightly going into the more technical details of power system. But then because we have spent enough time dealing with the fundamentals, I feel and I think that this is going to be very easy for you to. In fact, compared to the previous classes, today's class, that is bus admittance matrix, will be comparatively very easy class actually. So, but then every time there is a exam and everything, at least on this topic, you will get a question that is, given a small network, how do you form the bus admittance matrix? So what is, or it's also called Y bus matrix. So this is going to be easy, but then still, if you follow proper procedure and then understand it well, then it is easy. So otherwise, it is again going to be difficult. So with that brief overview, let's begin our class. So if you go to the previous lecture, so let me open that. Just give me a minute. I'll open the. On the left side, there is a generator and there is a bus bar, then followed by two transformers, T1 and T3. Then T1 transformer is connected to a transmission line, and similarly T3 transformer also connected to another transmission line. And other end, again we are stepping down and then finally connecting common bus bar, which is serving to a motor M. So this is a very simple or very basic power system network. The actual power network may have, as we already discussed, hundreds of generators and thousands of motors running continuously. So after solving this per unit example, again, I hope you had practiced this. I hope you had worked out how to do this. After solving this per unit example, so we divided it into regions. So we have 4 regions for this. And once it is divided into regions, we have converted the percentage impedance to the common impedance base. And finally, we got a circuit something like this. And this one, we were calling it as a reactance diagram. So this is the reactance diagram that we were calling. So if you look at the structure of this reactance diagram, basically this is like a graph. Okay, so that is what we will be our starting point today. We are making it more formal now in terms of that. So let me just take this structure. So what I do now is I'll just make a copy of this. From the last lecture, and now I'll come to the today's lecture. Reactance diagram. From lecture 9. So now when you look at this diagram, so if you remember that the generator, and this is the reactance of the generator, and there is a bus bar here. So then there is a transformer. After the transformer, there is a bus bar. There is another transformer, then there is a bus bar, and 2 transmission lines between these two. And finally, near the motor, there is another bus bar. So these are the bus bars we are considering. So let me give some numbering. So let's call this bus number 1, and let's call this bus number 2. Let's call this 3, 4, 5, and 6. So we have a 6 bus network. So how do you recognize a bus? So whenever 2 or more components are interconnected, then we call it as a bus bar. So for example, this is transformer. Transformer is connecting to the transmission line. So transmission line is one element, transformer is one element. Therefore, their connection here, I put a bus bar. Now what about this one, the R and L? Here I am not putting a bus bar because this entire is one single element. Coming to this side, this is a transmission line and this is a transformer. 2 different equipment when they are interconnected, then there is a bus bar connection here. Here at bus number 6, actually there are three different uh, equipments are connected. So that is transformer here, another transformer here, and another motor here. So this is a generator and this is a motor. So, at this bus number 6, three equipments are being connected. Similarly, at bus number 1, three equipments are connected. At bus number 3, two equipments are connected, and so on. So, how to identify buses? So, when two or more primary power system equipment are interconnected, a bus bar, a bus or a node is. So node is a general word. Mathematics people use node, but electrical engineering people call it as a bus or bus bar. So that is the case. Now, on the other end of the generator, what happens to this terminal? Remember, this is a three-phase generator. A three-phase generator will have three outgoing lines which are connected and maybe a one neutral grounded line. So this part is actually grounded here. Similarly, this network is also, generator is also grounded. So it is also customary to just give one node for this called node 0. So node 0, it is considered as a ground or reference bus. So we don't count that. So basically, what is the size of this system? We call it as a 6-bus system with one ground. So that is about this. So say, what about ground? So here I can say the grounding points of various equipment are combined together as a reference bus, and given the number 0. So of course this is not strict, so you can always give bus number 1 as my reference bus, and then you can always do like that. So this is not a very strict rule that everybody has to say always 0 bus is a reference. Okay, so let me not always reference is 0 bus. Just this is a simple note. So now I'd like to draw this in a different structure. So you see 1, 2, 4, 3, 5, 6 like this. I'd like to draw it as a graph. So slowly we are coming to a little bit more fun, abstract concept. Let's draw the above network as a graph. So what is a graph? So graph is nothing but collection of nodes and links. So I'll show you the example below. So we have 6. So this is 1, this is 2, this is 3, and this is 4, and this is 5, and this is 6. So this is the structure that we had in the above power system network. So the nodes are given the labels 1 to 6, and then what are the connections? So 1 is connected to 2, 2 is connected to 4, 1 is connected to 3, 3 is connected to 5, 5 is connected to 6, 4, 1 is connected back to the reference. And this node, we are calling it as a reference node. So this is the graph kind of a structure. So it is advantageous to represent your power system in the form of a graph so that we can analyze. There's a lot of mathematical analysis behind graphs. So a branch of mathematics dealing with study of graphs is called graph theory. So this is a very, very big branch of mathematics, and a lot of mathematicians are doing research in that area of graph theory. So as power system engineers, we will try to borrow some of the mathematics that they have done and apply it to our analysis of our power system networks. So this is about that graph. So look at the network we have and look at the graph, simple graph we have made. So for this graph, I can again define some parameters. Okay, so what are the parameters we can define? So we can say each node will have some voltage. So electrical parameters can be defined in the graph above. So for example, related to nodes, so we have node 1, 2, 3, 4, 5, 6. So what are the properties we can define? This is a voltage. So V1 at an angle of delta 1, V2 at an angle of delta 2, and so on up to V6 at an angle of delta 6. So like this I can define the voltages. So this is for the nodes. Now you can also define what kind of equipment is connected. So for example, at node 1, a generator is connected. At node 2, in fact, node 2, we cannot say a transformer is connected because transformer is connected between nodes 1 and 2. So we have to make a distinction between what is the network and what is the connections to that network. So this, nothing is there. At generator 6, a motor is connected. So something like this. Now coming to edges or branches or links. So branches. So what are the branches in our network? So if you just recollect, let me just go here. 1, 2 is a branch, 2, 4 is a branch, 1, 3, 3, 5, 4, 6, 5, 6, and 1, 0 and 6, 0. So let me do the branches. So 1, 2 is a branch, 2, 4 is a branch, so 1, 3 is a branch, then 3, 5 is a branch, then 4, 6 is a branch, then 5, 6 is a branch. And the other two branches, they are basically connections to the generator and motor, that is 1 to 0 and 6 to 0. Strictly speaking, these two branches not considered as part of the network. Let me explain that later. So they are basically counted already here above, generator and motor. So what does branch 1 to represent? So what are its parameters? And what is the equipment? So parameter is, it will have a reactance. so equipment is transformer and it has some reactance. So let's again go to the top. So the reactance is J15.125, whereas the reactance is here J16.133. So J15.125 per unit, and for 13 it is J. I'm sorry. So these are the different parameters. So like this, you can define parameters for your network. So far, whatever I have discussed, so I've basically discussed what is a graph and how the graph is formed, how to convert your electrical network into analyze it. So of course, this is a generalized network. Generalized means I am not giving specific values, I am just working with some variables. So think of it as bus 1 and this is bus 2, and bus 2 is connected to bus 3, and there is also a bus 4. And bus 4 is connected to bus 2. So something like this. So imagine that this is your network. So now you can ask the question. I think I come to the end of the page. So let me just take this to the next page. Work like this. Now you can consider so that this is 1 to 2 is a transmission line, 1 to 4 another transmission line, and 4 to 2 another transmission line, and 2 to 3 another transmission. So we have a 4 line network. So now you can ask a question, what about loads and generators? So the answer is they may be connected. So let's say at bus number 1, there can be a generator. So let me temporarily draw a generator. At bus number 2, there can be a load. At bus number 3, there can be another load. At bus number 4, there can be a generator. So this can be one kind of distribution, generators and loads. Or I'll just say another kind of distribution. Maybe at bus 1 there is a load, at bus 4 there is a load and a generator. Similarly at bus 2 there is a load, and at bus 3 there is a generator. So that is possible again. It's a different kind of network. So, so basically what you see is there's a network is there, and then at different buses and at different nodes, generators and loads are distributed. So this is another structure. So right now, so what I'll write here is at this stage, we focus only on the network and not worry about external connections. So what do I mean by external connections? The external connections are generators and loads. Generators and loads. So the bus admittance matrix we want to define for this particular 4 bus network. So let me write down the parameters also. So here Z12 is the per unit impedance of the line from going from 1 to 2, and this one is Z24, and this is Z14, and this is Z23. So these values are all per unit impedances of the transmission lines. You know how to calculate the per unit impedance. You know the actual impedance of this line, then you know the rated voltage level of this line, that will become the base voltage, and then the base MVA will be like 100 MVA or something like that, you can choose, and based on that you can determine the per unit impedance of the line. So this per unit impedance will have resistance and reactance both. So these parameters are given. Now, what you can do is you can write a simple Ohm's law. So what is Ohm's law? Ohm's law is nothing but V equal to I into Z. So V is a vector, I is a vector, and Z is a vector. So, or these are all complex numbers. So this same thing, I want to write it in a different way. So Ohm's law. So Ohm's law for transmission line. So consider a transmission line like this. Let's say this is bus number I and this is bus number J. Therefore, this impedance is Zij. Now I am interested in the current Iij. So, and you know the voltage here is Vi and the voltage here is Vj. So simple Ohm's law for a transmission line, how it will be? Vi minus Vj is equal to Iij Zij. So the difference of voltage is nothing but the voltage across this line, that is nothing but the voltage drop of the line. So this, I think, again you are familiar with this. Now make sure that the signs are correct. So for example, the current going from bus I to bus J is considered as positive. So therefore, from bus I to bus J, if it is positive, then Vi minus Vj will be here, not Vj minus Vi, and that will be Ij into Zij. Now, what is the next step? So the next step is, I can write like this. Next step is, let's look at our network. So if I look at our network, I can write I12, and this current is I14, and this current is I24, and this current is I23. So now we got a directions also. Now you can get a doubt why the current is I23 and not I32. So it is a matter of your choice. You can define any direction. So if the actual direction is going from 4 to 2, then whatever value you get here, that complex number, you just rotate it by 180 degrees and you will get the correct value. So these are all assumed directions of the current. So you can still calculate it and you get the answer, and the answer will tell you what is the actual direction of the current. So now once I know these directions, now come back to, let me again copy this so that it is convenient. Now KCL at bus 1, you will find that this current is going out, this current is going out, but you should also remember that there may be a generator or load here. So I will write like this, I1. So if there is generator or load, then there is some value for I1. If there is nothing is there, then I1 will be equal to 0. So similarly at bus 2 also I can consider current I2, and similarly here I can consider current I3, and finally at bus 4 I can consider I4. So what is the definition? So definition of currents. Let's say IK is the external current entering into bus K. So it is the external current. We are not calculating the internal current. So what are the internal currents? So I12 is internal current, I14 is internal current, I24 is internal current, and all these things. So for example, I K P. So is the internal current, or let me call it, is the current flowing in the transmission line connecting bus K and P. So that is the notation KP. So for example, I24 is nothing. So with these definitions, now if I write Kirchhoff's current law at all 4 buses, so KCL at all 4 buses. So I1 equal to, I2 equal to, I3 equal to, and I4 equal to. So let's look at our network. So what is I1 equal to? I12 plus I14. Just a simple incoming currents equal to outgoing currents. So this is I12 plus I14. What is I2? So net current injected into the bus 2. So I2 is what? You should be careful now. I12 is coming into the bus, so it will have a positive sign, or it will have a, on the right side it will have a negative sign. So outgoing currents I will consider as positive. Or to avoid confusion, let me do like this. So I'll just go back. So currents entering the bus are positive, current leaving the bus are negative. So therefore at bus 1, so what we have is current entering is plus I1 minus I12 minus I14 equal to 0. So this is one equation. Similarly at bus 2, let's look at bus 2. I2 is positive, I12 is positive, I23 and I24 are negative. So I get like this. I2 plus I12 minus I23 minus I24 equal to 0. The simple Kirchhoff's current law I am writing. Let's look at bus 3. I3 is positive, I23 is also positive, and it will be 0. So at bus 3, we have I3 plus I23 equal to 0. Similarly, we have at bus 4, I4, let me refer to that. So I4, then I14 will be positive, I24 will also be positive because they are entering the bus. So plus I14 plus I24 is equal to 0. So this is about the currents. Now I want to slightly rewrite this. So I want to rewrite it like this. I1, I2, I3, I4 is equal to I12 plus I14 minus I12 plus I23 plus I24 minus I23 and then minus I14 minus I24. So this I am writing it in the form of a matrix. So this is current, injection, vector. I'm sorry. So any doubts about this? Any doubts up to here? Ohm's law for transmission line. So here Ij is nothing but Vi minus Vj, and this is what we have seen as a Ohm's law for transmission line. So now I want to eliminate all the line currents. So how to eliminate that? I'll take this. So this, let's say this is equation A. And this is equation B. From equation A, I get the following. Vi minus Vj is equal to Iij into Zij. Now this Zij, I can bring it this side, so it will be dividing by Zij. Or you can write it as Yij. So what you get here is Iij is nothing but Vi minus Vj into Yij. So Yij is nothing but admittance, which is nothing but 1 by Zij. So just take the inverse of the impedance, you will get the admittance, and that will be multiplied here. So now if I want to write what is I12, I12 is nothing but Y12 into V1 minus V2, like this. What is I23 is nothing but Y23 into V2 minus V3. So it's a general structure. So what is I14 is nothing but Y14 into V1 minus V4, and so on, like this. So now I can also write these currents in this form. So if I make a vector like this, V1, V2, V3, V4, and then here if I want to write what is I12, so Y12 minus Y12, 0, 0. Okay, this is like this. So if you look at the first equation, so I12 is equal to Y12 into V1 minus Y12 into V2. So that is what we are getting here. So these two are same. Similarly, the second equation I can write it. So how to write a second equation? I23 is nothing but, first I will be 0, then it will be Y23 and minus Y23. And then finally it will be 0. So I get the I23 like this. So like this, I can fill up all the 4 branch currents. So now we got this one is the voltage vector. So now I want to combine the voltage vector and the current vector into one single equation. So this is the current vector I have. I want to combine it. So how to combine? So I12 I know already, I14 I know already. So I can just add them and finally I can get a vector. So let me go to the next page. So this is nothing but y12 into v1 minus v2 plus y14 into v1 minus v4. So like this I can write it. So is it clear? So this part I substituted here and this part I substituted here. So this is nothing, I14 is nothing but y14 into v1 minus v4. So any doubts on this? So any doubt up to this? So I'll write it as a row multiplied by column. So V1, V2, V3, V4. So in this expression, so there could be 4. So this is 1 row, 4 columns. This is 4 rows, 1 column. 1 by 1, that is an individual number, what is I1. Now in this entire line, V3 is not there. So the third element I'll put 0. So because 0 into V3, it will eliminate V3. Now what are the coefficients of V1? I have Y12 into V1 and Y14 into V1. So here I'll get Y12 plus Y14. This term will get multiplied with V1. Then look at the 2. So minus Y12 is here. That's all. So minus Y12. And the last one, V4 is here. So minus Y14. So like this. So how do you construct this row? So for the first row of this matrix, what you see, if you are interested in what is I1, just the bus 1 is connected to bus 2 and bus 4. It is not connected to bus 3. So you can put 0 here and put minus Y12 here and minus Y14 here, like this. And then the same elements again you add it and then keep it like this. So, so let's do it for I2. Okay. So what is I2? So again, if I copy from the previous, this one, I2 is minus I12 plus I23 plus I24. So this is I2. So this, how I can write it? This is Y12 V1 minus V2 plus what is I23? Y23 V2 minus V3. And what is I24? Y24 V2 minus V4. Just by looking at it, I can substitute it. Now if I want to write it in the form of a row, so let me make some more space. So what are the coefficients of V1 in this? So you see V1 is coming here, so minus Y12. I'm sorry. Coefficient of V2 we'll see later. What are the coefficients of V3? Minus Y23. What is the coefficient of V4? Here, minus Y24. And finally, what is the coefficient of V2? So here minus into minus will become plus. So I have plus Y12 plus Y23 plus Y24, like this. So this whole element is the second element of this row. So like this, I can write for I3, I can write for I4. So let's do it. So what is I3? So if I refer to my previous, I3 is minus I23. So very simple. That is nothing but minus Y23 into V2 minus V3. That is nothing but V1, V2, V3, V4. And this one will be, the V1 is not there, so 0. V4 is not there, so 0. And for V2, it is Y23 with a minus sign. And last row, what is I4? So can I ask you to try? So I4 is, what is I4? So minus 2, 4. So can you write it in this form? So this is again obvious, minus Y14 into V1 minus V4 minus Y24 into V2 minus V4. So can you write it in this form? V1, V2, V3, V4. So what is this? So can you try how writing like this? So I have did for bus 1, I have done for bus 2, I have done for bus 3. Bus 4 I am giving you to just try it yourself. So minus Y14 and then minus Y24, 0 and then finally Y14 plus Y24. Okay, so this answer is from AKRG and then Potti Sri Ramulo Engineering College. So this is correct. So finally, if you notice all four, we have a similar structure, just that they are rows. Okay, so this is row 1. So I can call this as row 2. I can call this as row 3. And finally this as row 4. So if I just copy it like that, so V1, V2, V3, V4. I'm just writing these lines so that this is I1, I2, I3, I4. So yeah, so row 4, I can directly just above it is there. So I'll write row 4. So minus Y14 minus Y24 0 Y14 plus Y24. That's it. So what is row 3? If I go up and find row 3, 0 minus Y23, Y23 0. So 0 minus Y23, Y23 0. So now if I go to I2, so what is I2? So minus 1, 2, minus 2, 3, minus 2, 4. Okay. So minus Y12, minus Y23, minus Y24. And this one is Y12 plus Y23 plus Y24. Similarly, if you go to the first line, so I have I1. Okay, so that is 1, 2, 0 and 1, 4. So y12 0 and then y14, and this is with minus sign, and this one will be y12 plus y14, like this. So this way you are able to complete the matrix. So what is the structure of this? So this one I can call it as I bus is equal to y bus into v bus. So this is the current injection matrix or vector admittance matrix, and this one is the bus voltage vector. So what is the size of it? So this has n rows, one column. What is the size of this? This has also n rows, one column, and this one is n rows by n columns. So like this you get the bus admittance matrix. So any doubts here so far? The above method is long process, is long method. So what you have to do is KCL at each node and then Ohm's law. So is there a shortcut method? To form Y bus? So the answer is yes. So what you do is just look at the network and you can write Y bus. So look at this. So let me draw our network. So do you remember our network? So if I go up, I think the network is in page 2. Let me copy this. Now what you have to do is, so here I will draw the Y bus. So I'm just making a table so that I can write the matrix easily. So this is my Y bus. So the technique is, I'll just give the numbering. This is 1, 2, 3, 4. Similarly, rows also, first row, second row, third row, fourth row. So first what you do is, first you worry about the off diagonal elements. This is a diagonal element. This is another diagonal element, like this. So diagonal elements, you forget it. First go for off diagonal elements. This is what? First row, second column. Is there any line connecting 1, 2? So you look at this 1 and 2, there is a line connecting. So just put a minus sign and write y12. Is there any line connecting 1, 4. Now look at the diagram. Yes, there is a line connecting 1 to 4. So it is minus y14. Is there any? So there is no line between 1 and 3. 1, 3 direct connection not there. So 0. And 1, 4, I have minus y14. So this row you copy to the column. So same you copy it here, and this y14 you copy it here, minus y14. Now come to the second row and look at the bus 2. So is 2 connected to 1? Yes, already we had. 2 is connected to 3. Yes, 2 is connected to 3. So y23 with a minus sign. Is 2 connected to 4? Yes, 2 is connected to 4. So minus y24 with a, of course, with a minus. These two you can copy it here, minus y23, minus y24. So now come to bus 3. Is bus 3 connected to bus 1? No. So 0. Is bus 3 connected to bus 2? Yes, 2, 3 are connected. So already y23 it is there. Now this will come back later. Is bus 3 connected to bus 4? Direct connection not there. So therefore it is 0. And this 0 we can copy it here. Now only the diagonal elements are remaining. So how to do the diagonal elements? Just add these two and remove the minus sign. So whatever is there in this row, y12 plus y14. So y12 plus y14. Again add all these three elements. So y12 plus y23. So like this. Again add all these three and remove the minus sign. So you'll get y23. Again add all y23. Now if you look at this y bus is exactly same as the y bus that we got above. So this is the shortcut method. So this y bus and this y bus are exactly same. So whatever we have here, the same data we'll have here also. So this is the shortcut way of drawing the y bus. Just look at the network and you can write it. Any doubts about this? So example first, okay. Form y bus for following. Network. So the network is like this. So this is bus 1, this is bus 2, this is bus 3. And the impedance of this is Z12 is J 0.1 per unit. Z23 is J 0.2 per unit. Okay, so this is the question. So I will solve it for you. So answer. So what is the first step? Find admittances. So what is y12 is nothing but 1 by z12. That is nothing but 1 by j 0.1. That is nothing but minus j10. Okay. So what is y23? 1 by z23. That is 1 by j.2. That is minus j5. So step 1 is completed. We have found out what is the y12 and y23. Now, step 2, just form the this is bus 1, this is bus 2, this is bus 3. So Y12 is minus J10. I'm sorry. Y23 is minus J5. So simply you can write it Y bus. So Y bus will have 4 elements, sorry, 9 elements. So the diagonal elements you forget about it. So this is 1, this is 2, and this is 3. This is row 1, row 2, row 3. Between 1 and 2, there is y12. So already there is a minus here. So this is actually minus y12. 1 and 3, no connection. So 0. So minus y12, 0. Between 2 and 3, there is minus y23. And just add them and reverse the sign. Add them and reverse the sign. Y23 plus y12. And then y23. So this is our y bus. So this is nothing but, so y12 is minus j10, y minus 12 is plus j10, 0. And what about this one? Minus y12 is plus j10, and this one is y23 is minus j15 and plus j5, then 0, and y23 is j5, and finally this one is minus j5. This is your y bus. So any doubts on this? Form y bus. So the network is like this. So directly I'll give so this is the question. So can you try this? So you get it minus of minus j5, so you will get plus j5. Now is 1 connected to 3? So 1 directly not connected to 3, so 0. Is 1 connected to 4? 1 not connected to 4, so 0. Is 1 connected to 5? Yes. So minus j6 will become plus j6. Then copy this like this, j5, 0, 0, j6. This entire row, I'll copy it as a column here. Next, looking at the second row, is bus 2 connected to bus 1? Yes, already that is written. 2 is connected to 3? Yes, so J10. So I'll put J10 here. Is 2 connected to 4? Yes, it is connected. So J7. Is 2 connected to 5? There is no direct connection. So 0. These three elements I will copy here. J10, J7 and 0. Next. Is already it is there. 3 is not connected to 1, 4 and 5. So this will all be zeros. So this also will be zeros. Is 4 connected to 5? The answer is yes. So this is J10 and this will also J10. And we completed all the off diagonal elements. So now how to get the diagonal element? Just add all the row elements. So J5 plus J6 is J11. So you put a minus sign and J11. So add all of them. 15, 15 plus 7 is 22. So minus J22. So this is just 10 is there. So minus J10. And then finally here 17 is there, minus J17. And finally here 6 plus 10, this is minus J16. So like this, you get the Y bus for this above network. So is that clear? So let me just cross check, do I have any mistakes? Form Y bus for following network. So the system is like this. So here Y12 equal to minus J7, Y23 equal to minus J10. So this is bus 1, this is bus 2 and this is bus 3. But the problem is at bus number 1, a generator is given. So the voltage that is generated is 1.05 at an angle 0 degrees per unit. And this is so the reactance is J0.1 per unit. So for this network, an impedance is also given. So how will you solve this? In fact, I can also add one more reactance here. Or, okay, let me just not worry about that now. Just how will you solve this? So since we have about 10 minutes left, let me write down the answer myself. Let's answer this. So what you do is simply do the old method, the long method. So a voltage source in series with the impedance, you can replace with a current source in parallel with the impedance. So that is like the Norton's equivalent. So do you know Norton's equivalent? You can just replace a resistance with a current source. Look at the source at bus 1. So you have we have V equal to 1.05 angle 0 per unit, and this is J, this is your reactance. So just find Norton's current. So which is nothing but just the short circuit current. So if you just short circuit this, what is the current? So I equal to 1.050 degrees divided by J.1. So that will be 10.5 with minus J. So this is I Norton's. So you can actually replace this with a network like this. Minus J 10.5 per unit in parallel with. So this is your bus 1 and this is your J 0.1. So this is X. So if I represent it as a Y, then it will become minus J10. That is, the reactance will be minus, admittance will be minus J10. And this is your grounding. Now after this bus 1, what you have? You have some bus 2 here. So here, if you write KCL at bus 1, so what you will get? So I1, so I1 is the external current being injected. So if you denote that as I1 like this, so I1 will be equal to, so all current entering will be positive. So plus, so because it is minus J10.5 is the current here. And then this one, it will be, this one if you say I10, then it will be like this. So effectively what happens is this will get added to the Y bus. So, minus I10, so this is I10 and this one will be I12, minus I12 equal to 0. So I10 is nothing but I1 minus J10.5. This is nothing but V1 Y10 and this is nothing but Y12 V1 minus V2 equal to 0. So basically this particular minus Y10 is adding extra to the Y bus. And then this term is coming anyway. This right now we don't worry because it is not affecting the Y bus. So therefore Y bus is nothing but so first look at the network. So 7 and 10 is there. So just as if it is not there, so I'll just write it J7 and 0. So this is 1, 2, 3. This is 1, 2, 3. This is J7 and 0. So whereas here, here it will be J10 and here it will be J10 minus J17 and this will be minus J10. So here minus J7 minus J10 will come into picture. So this is just the additional element that is coming. So finally it will become minus J17. So this is your Y bus. So today to summarize in our class, we have discussed how to form the Y bus. So given any network, how you can form the Y bus we have seen. So we'll take up more examples in the next class about this. Now, before just concluding the class, I'd just like to give you one homework. Any doubts up to here? So this is, let's say, challenge homework. Consider a simple network. So the network is like this. So here the voltage is V1 and the angle is delta 1. Here the voltage is V2 and the angle is delta 2. And this reactance is J1, or let me call it J5 ohms. So the question is like this. So this is question 1. I'm sorry, I just want to change this a little bit. So this is V1 angle delta 1, and here I connect a simple load. So load 10 plus J5 kVA. So this is kilowatts and this is kVAR. So the load is given. So here the voltage is V2 angle delta 2. Here the voltage is V1 angle delta 1. And this is J5 ohms. So I have two questions here. So question 1, given V2 delta 2 equal to 1000 angle 0 degrees, find V1 delta 1. This is question 1. The question 2 is given V1 delta 1 equal to 1000 angle 0 degrees, find V2 delta 2. So basically the network is same, just that once V1 value is given, find out V2 value. Other case it is given. So what you will notice is that this is very easy, and this one is very difficult. So try to solve this problem and send me your answers. So email your answers to. So I have given two homework questions, Q1, Q2. So just try these two. You will find that the question 1 is very easy and question 1 is very difficult. Question 2 is very difficult. So, but then try both of them and solve it, and then you can send your answers to me. So whoever gets correct answer for question 2, in the next class I will mention them. So this is open for all the students who are listening to this lecture. So with this, I think I'll conclude today's class. So let's meet in the next class. In the next class also we'll discuss Y bus a little bit more, and then we'll conclude it.